Hello, I want to talk to you on how to solve for the motion of such a system. We have here a mass M in an incline, mass M1 and M2 and a pulley with friction, and we want to solve for this type of system. Find the acceleration of the system. We assume it is um, uh, moving and certain equilibrium. It is moving, and we want to find uh, what is the acceleration of the system. So I put here all the formulas we need to solve for such a system. We have here force equal m times gravity. Also we have here force equal friction coefficient times the normal force. And we have here that also that the torque equal the inertia times the angular acceleration. And the inertia of a disk, which is the pulley, which is rotating with respect to its center of mass, is half mr squared. And here it's a formula that says what is the inertia of a mass. Let's say we have a point here and we have a mass that is going through a circular motion around this point at a distance d. And we have a mass m. Basically, it says that the inertia of the system is md squared, and this is are the formula used that are from like Newton's laws that derived from Newton's laws. So let's draw all the forces acting on the system. We have here weight 1, weight of mass 1. We have the normal force. We have friction. We have weight 2. We have here the mass of the pulley and the normal force here that is acting. So basically we can see here that all the forces that are perpendicular to we assume the system is moving this way. So the forces that are perpendicular to the motion path, they don't contribute to the motion, so we don't need to calculate them. So we don't need the normal force. This here is not used. This here is not used, and this one is not used. And basically we have tension here, the tension, which are the ropes. We need to add. So basically now let's go to the next slide and we'll just draw all the forces that really are contributing to the motion. So basically we have here friction, which is mu times m1 times g times cos theta, and we have here theta. And we have another component of the force, which is also the m1 times g, which is the weight, times sine theta. And we have here m2 g. We have any other forces? No, because okay, we also have the tensions here, but what I want to show here is that these are the forces really that are in the path of the motion, and they contribute to the motion. But I want to show a method here that we can use to make the calculation without going through all these forces at the same time. Basically, we say like what this rope does, it brings the mass m1, which could be like modeled here as a mass here at radius r from the center here. So m1 will be here, and we have also what this rope will do is just bring this mass here and put it here, which is a mass m2. Okay, so basically we have, if we draw it here, we have m2 and we have m1, and basically the forces that are acting on m1 we can factorize, so it's m1g mu cos theta plus sine theta. And basically here it is m2 g, and we have here the radius r. Okay, so this is an equivalent system or a model that we're going to use to to find the acceleration of the system. Okay, that's all we need. So let's go to the next slide. So we have here, let's say what we said here, that we have the first force here and the second force here. We have M1 and we have M2. Okay, so let's first find what is the sum of the two forces that are acting here in the rotation. So there's this force that is rotating this way, and there is another the other force rotating this way. So the net force will be F equal M1 G sine theta plus mu cos theta. And since we said that the system was moving this way, we're going to put a minus sign on this force. We need to add to it M2 G, which is the other force acting on M2. Okay, the torque will be, if we look at the torque, will be F times the radius. This will be the torque, so we need to multiply all this by the radius to get the torque. Okay, and for the inertia, we have the inertia, which is the inertia of the disk that we said, which is half of m r squared plus m1 r squared plus m2 r squared. Okay, and we said that torque equal ACM times inertia. So ACM becomes, if you want to derive ACM, we need to divide torque by inertia. So divide torque, which is this one, is the torque, by the inertia, which is here. So we're gonna like have one R that's gonna disappear. So the basic ICM will be M1 G sine theta plus mu cos theta plus M2 G divided by, and we factorize R squared, half of M plus M1 plus M2, and multiplied here by R. And this is actually the what we have here is the angular velocity. So we have a system that is rotating this way. So we're checking the angular acceleration, and if you want to know the acceleration, let's say of mass M2, which is rotating down here, we need to multiply it by R, which is the radius. Okay, so we need to multiply ACM by R, so this will cancel out, and then we have this. This is really the formula that we have for an incline with friction with a pulley that has mass and two masses M1 and M2, and you can see that it is much easier to make these calculations. With this, we're making an equivalent mechanical system to estimate the acceleration.